Hello, and welcome to the 7th clinic in linear algebra. Today, we are going to be looking at LU factorization or LU decomposition for a matrix and how we can use this to solve a system of equations. So we're asked to find LU factorization for this matrix A. So what we do is first start with the matrix. And we're going to perform row operations on this. And what we're going to do is we're going to try and only use the third type, right? So we're not going to switch rows, and we're not going to multiply a row by a constant. So all we're going to do is multiply a row by a constant and add it to another row, right? Type 3. So let's start by getting zeros under the 1, 1 entry. -2 row 1 plus row 2, right? And then row 1 plus row 3. Right? Because the idea is what we want to do is make this into an upper triangular matrix. Well, now what we want to do is make the entry below 2, 2, 0, and that is done as 5/2 row 2 plus row 3. We now have an upper triangular matrix, so what we do is we say, okay, there is our U. For L, we want a lower triangular. Right? So set up a lower triangular where the main diagonal are all ones. The idea now is we have to fill in the missing pieces. And they are easy to do, right? For the 2, 1 entry, what we do is we go back and we look at how we determined U. What did we have to multiply by to zero out the 2, 1 entry? We multiplied it by -2. That becomes +2. For the 3, 1, what do we have to multiply by? We multiplied by 1, so that becomes -1. And then for the 3, 2, we multiplied by 5/2, so that entry is -5/2. So there's our L, and there's our U. Again, start with our matrix, and we want to try and write it as an upper triangular. We would have -2 row 1 plus row 2, and then we would have 5 row 1 plus row 3. And that would leave us with this. Since we are not allowed to switch rows, we have this 0 here. It is not possible to write this as an upper triangular. So an LU decomposition is not possible. Right, now, how can we use this to solve a system of equations? Well, let's go ahead and take a look now. There it is. So what we do is we set up our coefficient matrix. And we write an LU decomposition for it. -2 row 1 plus row 2, 3 row 1 plus row 3. Then 4 row 2 plus row 3, actually -4. There is our U, our upper triangular. Then L, right, would be -2, -3, and +4. Okay, so there is our U, there is our L. Now what we want to do is we want to solve this system for Y, right? Well, we have our L, right? There's our Y vector, and then our B vector, right? Our constant vector, we look back, it's all ones. Now notice what we get here, right? Y1 equals 1. 2y1 plus y2 equals 1. -3y1 plus 4y2 plus y3 is equal to 1. And then what we do is we do like forward substitution, right? Y1 is 1, okay? So 2 times 1 plus y2 has to be 1, right? So 2 plus y2 is 1, which means y2 has to be 1. I'm sorry, -1, even. Then we plug those in for the last equation, right? So we get -3 plus 4, which is 1. I'm sorry, not plus 4, it's -4. So -3 minus 4, -7, plus y3 has to be 1. That means that y3 has to be 8. Now, we set up the equation ux equals y and solve for x. And that x vector is our solution vector, right? So u times x is equal to y, which we just found. This will give us x1 plus 2x2 plus x3 is 1. Negative x2 plus x3 is -1. And finally, x3 is 8. And now we do just simple backward substitution. right? So negative x2 plus 8 is negative 1. That means x2 has to be 9, right? So then we get x1 plus 18 plus 8 is 1, right? So x1 plus 26 is 1. So x1 would have to be negative 25. And so our solution is the ordered triple, negative 25, 9, and 8. Let's do 2 more just to hammer this home. But this time we're going to look at larger matrices, right? So we're going to look at a 4 by 4 and then a 4 by 4 system. Now, the only thing that's different is the size. The process is the same. We want to try and get this into upper triangular. Row 1 plus row 2, negative 3 row 1 plus row 3, negative 2 row 1 plus row 4. Then negative 3 row 2 plus row 3, and then row 2 plus row 4. Right? And remember to always keep track of what you're multiplying each row by. And finally, negative 3/4 row 3 plus row 4. All right, so there is our U. All right, so now for the L. Again, you set up a 4 by 4 matrix with 1s along the main diagonal, 0s all above it. Now we need to fill in the missing pieces. Let's start with column 1. 2, 1. So it'll be negative 1, 3, 2, right? Negative 1, 3, 2. Column 2, the missing pieces, we're going to get 3, 1. And then, I'm sorry, 3, negative 1. Right? And then we're finally going to get 3/4 here. Right now, we're just going to look at a 4 by 4 system. Set up the coefficient matrix. 2, 2, 1, 0. 3, 0, negative 1, 1. 0, 1, 0, 5. Negative 1, 1, 0, 0. All right, let's go ahead and decompose this. Negative 3 halves row 1 plus row 2. 1 half row 1 plus row 4. Next up, 1/3 row 2 plus row 3. 2/3 row 2 plus row 4. We now need to do negative 7/5 row 3 plus row 4. So there is our U. Our L will be 3 halves, right, for this position here. Negative 1/2 here, right? And notice we didn't have to do anything to zero out row 3, right? So that entry is just 0. Then we get negative 1/3, negative 2/3. And finally, 7/5. Right, now we want to solve Ly equals B. Okay, I'll let you, the dear viewer, do the work. You should get this. Right, so we can use that to do this. Right, now we solve this for x. Okay. And again, I'll leave it up to the viewer to do the actual algebra, but you get a ordered, what is a quadruple? -4, 10, -2, -1 as the solution. Okay. Right. So that concludes this clinic on LU decomposition. Right. The next clinic, we will start looking at determinants. Okay. I will see you all then.